Okay, so in this talk, I'm going to talk about some of the recent work that I've done over previous years, as well as some ongoing work and some inspirations of mine as well. And my goal here is some of this material may be familiar to you if you've heard me talk recently, and some of it might be new. And I hope to inspire and also advance some important areas for this field that I think will be useful for us to consider going forward in discussions, after talks, in the workshops, and so on. So starting with this question of what are teams? Well, it's pretty interesting that I'm the first one talking explicitly about teams today. So it's good that I have this definition. So generally, when we think of teams, it's a group of individuals that work together with each other. They often use technology. Team members also have specific roles. They often take on different roles and they don't do the same types of things. But one common thing is that they're all working towards a shared goal. And when we think about teams, we know that they're context specific. There's an individual working with their technology within a broader group of the team that may be situated within an organization. And what's important here is that much of the work focusing on studying team cognition or teamwork focuses on things that are going on within team members' heads and ways to measure that. But recent efforts have actually advanced some pretty compelling theory that says we don't really need to look at what's going on in the head of team members, because we can understand their cognitive work that they're doing by focusing on the actions and interactions of the team members. And this is interesting because, well, if we think about the cognitive work that many complex teams do when they're solving problems, developing, rockets to go into space, this is pretty cognitively challenging work. But if we think in particular about, well, let's human interaction more generally, rather than this complex cognitive work that teams do, this also quickly becomes pretty complex. So there's a lot of things, especially as wearable sensors get used or more readily available, and algorithms for processing things like video. Let me just turn on my laser pointer here. Nope, that's not working. Yeah, so we can extract a lot of things from video with some basic computer vision or things like OpenPose. We can use accelerometers. We can process signals from the speech, whether that's the actual words that people say versus fundamental frequency or other properties. We can look at physiological signals, neurophysiology, questionnaires over time. This is, for example, mouse movements, which you could also observe for teams. And then this doesn't even begin to address the complexity we have when we're all virtually interacting. So one of the approaches that I think that we really need to advance is this area of social coordination dynamics. And this is essentially a scientific approach for understanding coordination, where teams in particular are a subset of a social context. So to get a better idea of how to cope with this richness of human interaction and how we might be able to better understand teamwork, I'm going to unpack each of these terms, starting with the social. So one of these aspects of social interaction is that there's a mutual information exchange between people who are interacting, and it's thought to be multiscale. So a simple example of something that's multiscale is a sort of nested frequencies within a signal, although there's many other examples that I'm going to bring up throughout my talk. And this was also why I was asking my question earlier about this difference between sensory motor communication versus information transfer, because I thought that was interesting and related to my perspective. But we know that when we're thinking about teams who need to collaborate, if they want to be effective, coordination needs to span behavior, the things that they're doing, and their knowledge, the things that they know about. And this can occur spatially and temporally. We know that teams don't just do their work instantaneously, it happens over time. And this kind of coordination can happen within an individual, as we saw some examples of earlier, but also between individuals. And there's this inherent multimodality to it that we don't have a great understanding of yet, that coordination happens between physiology, body movements, language, and even technologies. So coordination, if I were pressed to define it, it would be the ways in which components and processes of a system change together over time. And I think that there are many forms of coordination. So things like alignment, which is the theme of this conference, synchronization, co-regulation, and coordination is the sort of superordinate construct here. And we can get more specific than that. And I'll talk a bit more about that as well. But we can think of coordination as how pendulums on clocks hanging on a wall synchronize, how metronomes tend to synchronize as well, or how team members in a rowing crew move in time together. But when we're thinking about teamwork specifically, the functionality of why people are coordinating their behavior and knowledge and how that's related to different aspects of the teamwork, it's not that clear yet. So another aspect of this approach is dynamics. And this implies that we take a systems approach to studying teams. And there's many components of a team. There's components that are also hierarchically structured. So we could think of different subsystems, different physiological systems within an individual, for example, and how that scales up to multiple teams who, again, may be nested within an organizational structure. But the key aspect here is that the relationships and the interactions between these components change over time. And that's interesting and important to us. And the strength of that coordination can change, and maybe it even breaks down altogether. And that's one of the kind of guiding themes to some of the work that I'm doing now. There's also this other aspect that, that these are open systems, so we can't just say teams are closed off to their environment. There are things, unknown events that happen, perturbations, things that can influence the system that aren't due to intrinsic properties of the team as a system, but extrinsic. So I want to make this kind of forms of coordination a bit more explicit. And I think there's two kind of key types of coordination that, that I'm going to talk about. One is about understanding that systems exhibit states. So when we think about human interaction, we know that we may have patterns of cognition, emotion, behavior, and physiology, and they can vary over time. But some of them are more stable than others. So coordination can be thought of as a degree of stability. And stability can also be how ordered or disordered a system is. So if we think about this kind of attractor basin, and the ball here represents a given state that a team might exhibit, it can move around a bit, but it's generally kind of ordered. But we know that we could also have extrinsic forces. There might be a surprise or a crisis scenario that rapidly changes the state of the team. So this is one type of stability or order and disorder that I see as a case of system organization. So one level of coordination. And there's a good example here from Damien Kelty-Stephen to make this perhaps a bit more concrete. If you're familiar with the Lorentz equation or the butterfly attractor, if you generate data from this equation and you calculate entropy across the time series, what you can see that during the startup period of the system, entropy, which reflects amount of order in the system, is relatively stable before a transition point starts to happen. And then we see this rise in entropy that reflects an increase in disorder before settling into a new pattern of the system where entropy begins to decline, and then it's totally stabilized here. So this is a form of system level organization, or a form of coordination, if you will. We can also think about component level coordination, which I think we've heard a few examples of today, where you have at least two signals. This could be two people, for example, and looking at how their emotions vary together over time. It could be musicians as well. And we could think about how, even at just a component level, there's different things like whether they are changing together in time or whether there's a lagged relationship and so on, or whether there's a change in overall level between these. And so when we're thinking about teams in component coordination, we may be considering things like pairwise relationships between each of the members of the team, but we might also be interested in sort of a global measure of the team's coordination. So this is my last part of the coordination dynamics overview in this talk. And maybe it's not something that I've thought through too well, but Essential to this area, which comes from ideas in physics and thermodynamics, is order parameters, which are collective variables that capture the current state of coordination in a system, and it also varies over time. What's nice is that these measures as collective variables can span multiple levels of analysis. And I think we're also going to hear a bit more about this in the next talk by Mingxin Zhang. But this helps us to simplify complexity in complex systems if we know what an order parameter is. And this is important in this case because a lot of studies that we think of that look at alignment or coordination are on rhythmic tasks. If we look at musicians, we know what the timing ought to be, and we know people ought to perform rhythmically. So it's generally more straightforward to think of order parameters that make sense in these cases. Whereas when we think of, well, how do teams work together to solve a problem? It's a bit more challenging to see what these order parameters are. Although in principle, it could perhaps be any kind of measure of coordination that we might come up with. The other aspect is control parameters. So different variations to a control parameter ought to influence the behavior of the order parameter. This isn't causal in a way that we would think of like Granger causality, for example, but it is deterministic that we know that the values covary systematically. And if we think about a simple control parameter here is temperature for a fluid, and we know that there's going to be a change in the system as a function of the value of temperature, for example, from gas to liquid. These haven't really been studied much in team coordination before, although Jamie Gorman and colleagues looked at how team familiarity changed their order parameter of coordination. Okay, so that's sort of the approach. And now I'm going to get into some more examples. What's important here is thinking of team coordination dynamics as a subset of social coordination dynamics that is an area that has a lot of variability. So there's a lot of modalities that people are studying, different methods, and they're specifying coordination in different ways. So I think we need to be explicit about each of these 4 dimensions, and I'm going to try to use this structure through the rest of my talk as much as possible. Before I do that, and maybe you've already heard me talk about this before, a couple studies I'm going to talk about used the Moonbase Alpha task, which was a serious game developed by NASA and some game designers. Essentially, we had dyads that performed this task together in a co-located space where they get 25 minutes of oxygen in the game to restore functioning to the moon base. This is a nice task because it's very easy to quantify their performance in terms of the time that they take to restore functioning to the moon base, the total percentage of oxygen which they restore, because not everyone restores it completely, as well as the number of objects that they repair in the simulated environment. This also allows us to group teams into how well they performed, from quite poorly if they didn't restore any oxygen to sort of some mediocre amounts to the highest performing teams that restore it quickly. So in one analysis of this data, we focused particularly on the modality of the semantic content of the speech. What we have here is a time series of collaborative problem-solving processes, things like generating information, requesting knowledge, referring to goals, trying to develop solutions. And these are all just turned into discrete categories based on the transcriptions and a coding system that we developed. We can use a method which is based on entropy and slide it across this time series to think about how much order or disorder there is in the system. And thinking about this example I showed earlier, when we identify peak points, this should indicate that there are transitions going on in the communicative processes. So the form of coordination here is about the relative amount of order or disorder in communication states. And this functioned in the way that we empirically observed that these transition points we identified separated distinct distributions of collaborative cognitive states, or the types of communication states within those so-called epochs or phases were actually distinct. One of our also interesting finding from this paper is that the values at the transition point, the lower the entropy values were, the better the teams ended up performing. So there's something that suggests sort of an optimal relationship between the amount of order at a transition point and how well teams would perform on this task. Using the same task, we also looked at the movement dynamics. So we extract bodily movements. It's a global measure of body movement for each of the team members, actually using a webcam that was facing the team members while they performed the task on the computers, using video frame differencing. And we quantify movement coordination in using cross-wavelet coherence. So this is an example cross-wavelet coherence plot, where you have essentially time across the task here on the x-axis. You have hot values or more red values corresponding to high coherence or high coordination, and cool values suggesting little to no coordination. What you have here is time scale. So these are very fast scale values, and these are very slow scale. And so what we see, for example, that this form of coordination is related to body movements, and that it emerged at a level greater than chance and task demands, particularly above this point. And this is just from one example team. And that this amount of coordination was actually related to performance, particularly those that were in phase at 1 second. What I find even more interesting about this study that we did was that the change in the coordination was actually systematically related to the task performance. So with some growth curve modeling, we showed that the lowest performing teams had this stronger quadratic trend in their change in coordination, the average coherence across several periods for the task, whereas the highest performing remained relatively stable, although they all seem to start out at about the same point and end at about the same point in terms of how coordinated they are. So I'm going to switch gears a little bit and think about what we need to advance team coordination dynamics research. I gave you just a few examples from my own work there, but I think we need to get better about incorporating multiple modalities, particularly in such a sort of interaction-rich domain. We need to work toward identifying drivers of change. So what might be those potential control parameters that we can influence? And it could also be that these are influential team members. And I'll give an example of this in a moment. We need to understand this functional effect that coordination has on teamwork. We also should consider this multiscale aspect. So I didn't get to talk about it too much in my last example, but we did see that some of these scales that we examined didn't have an effect on how well teams performed, even though they were coordinated to some extent, whereas certain scales mattered for predicting performance. And then we need to focus more on incorporating multivariate methods to study coordination in larger teams. So in the next few examples, one is not my own work, but I think it's a really cool paper. And one of the reasons about this, that I think this paper is really cool, is that it focuses on movements, speech rate, and changes in the user interface. So it captures many of these elements that we think are important for teamwork, especially the technological interaction. So they incorporate all of these modalities into a single analysis called multidimensional recurrence quantification. If we want to talk about this in terms of what form of coordination this is, it's sort of the regularity of temporal matching across all of these signals. So what you see when you look at points that repeat here in this recurrence matrix, you can identify when there's sort of stable patterns at the sort of system level across, with the system level being everything that's input into it. So from 3 team members' movements, speech, and their user interface. So the function of coordination here was they showed that actually less regularity in the signal was predicting better collaborative problem-solving processes for shared knowledge, as well as negotiation about the task. So this was interesting. And in another study, also not my own, but uses a similar kind of technique based on recurrence. This is some work by Jamie Gorman and colleagues, focusing here only on one modality, the speaker-only time series. And I already mentioned the method here, but this form of coordination is about the communicative regularity by focusing on how deterministic this speaker signals are. And we can see that here. What was really interesting here is that they identify reorganizations in the communication as a function of adaptation. So this example shows that there was a fire in this simulated healthcare setting, and the communication patterns and the ability to predict future states from this crossed a particular threshold in their method that showed, okay, we could pick up a critical reorganization here. And it was interesting because less experienced teams were also slower to reorganize and adapt to challenges than more experienced teams. Another aspect of this is that something I mentioned earlier, what might be a driver of changes in coordination. In this case, it was particular team members, so a surgeon and a nurse, who, by filtering out the contributions of each of the teams, they're able to show that this reorganization was no longer evident if you sort of exclude these key team members. So it's a nice empirical example to identify who are kind of drivers of change in the coordination. So this is another example from one of my recent papers with Aaron Likens, and this is just one of the examples where we were trying to think about this question of how can we model coordination when it changes over time and changes perhaps differently at different timescales. So we have this method which kind of integrates a few things that already existed in the literature to look at what we call windowed multiscale synchrony. What's nice about this is an example with some complex sine waves in our paper, which you can check out here. We include some other simulated signals as well as empirical ones, but this is the easiest one to illustrate this. So the sine waves, the two of them have these properties. So there's some higher power, for example, at these frequencies and at this frequency here. And in one of the other signals, we have only high power at this particular frequency, but it drops out. And we wanted to be able to showcase that, well, we can detect with our synchrony measure that these signals are synchronized at these particular frequencies and that we can detect the changes. Another aspect of this is it is based on distributions of relative phase values, which I don't have time to talk more about right now, but it captures sort of stable coordination patterns that don't have to be one-to-one, like perfect synchrony, but they can be sort of different ratios. So this is something that's quite flexible, and we hope to see it developed further. In another project, we're working with the sociometric badges. And this is just from a case study, which we have a preprint available on. In this case, we get the vocal amplitude data from 7 team members as they were working on a sort of lost at sea scenario. We use a measure called dynamic complexity, which also reflects the system order and disorder, and we can apply this to each of the signals individually, or we can look at some sort of global properties of the signal, and we could identify critical instabilities or potential transition points using this. What I'd like to highlight here is that we had some time points that we knew were changes in the task, like where things were getting set up, and we're just sort of testing how good these sensors work and these measures, doing an individual task, moving to the team task, and post task. And we see that we can actually recover our known transitions that we knew prior to analyzing the data. And we expected that there would also be sort of during task transitions or things that happen during the interaction, which we can see here. And another thing that we're trying to advance to better understand this is how the network structure, at least in terms of who it is that's speaking more and who they're sort of taking turns with the most, changes across these sort of identified phases for this task. Okay, I'm pretty close on time here, I think. So I'm going to wrap up with the last few points. So if we want to better understand the functions of coordination, we really should be trying to map coordination in different modalities to certain kinds of outcomes. This is a paper where we look at this in psychotherapy, but I'm really interested to see what we find in team coordination. Maybe this is certain modalities relate more to the actual task itself. Others might relate more to an interpersonal dimension like cohesion and trust, or common ground. And actually, one of my PhD students, Elvira Halgas, has a poster that I recommend that you check out in the virtual poster hall, where she's going to talk a bit more about our review of team coordination dynamics. And my colleagues, Dr. Josef Cavers and Kjerne van Eindhoven, were working on answering this question: how can we augment human performance in crisis scenarios with wearable technologies? And we're studying this in sort of stressful collaborative games as well as in a healthcare context. And my last slide here is just about wrapping up. So some of these needs that I think we have: when coordination is multi-scale, it spans a lot of modalities and we can use a lot of methods to study it. We really need to see how do these methods compare. So applying multiple methods to see what converges and what diverges and the meaning we would get from that, seeing what different forms coordination has as it changes over time. And in particularly, we need to have more efforts that can identify these potential control parameters so that we can influence teamwork to adapt in the ways that we think are optimal. And then understanding what function coordination has, we might need some better models to map these relationships, whether that's, again, task performance or other teamwork processes. So thanks a lot to Mirla for inviting me to speak, as well as my many great collaborators.
Thank you so much, Travis. And I knew you were just the right person to put in the slot today, because you've managed to pick up on a lot of points that have already been brought up, but also to introduce us to the theme of teams, which seems quite pertinent as it's in the title of the conference. So thank you for doing that. I want to just pick up on one point, or rather one term, which you called the drivers of change, which I thought was so pertinent to what we had been talking about with Bahadur and Anita, this idea of these switches, right, that make us do things like incorporate the opinions of others, or start taking on information about their coordination, their movement coordination patterns. We have a talk by Justin Sulik on Friday on Mavericks, which might be particularly interesting as well, who work outside of the team, but also manage to be a driver of change. So you might want to tune in for that. But I wonder, one point that I have been thinking about, which is you talked about these so-called experts, and there's data from Leonnoy who says something similar, that they make these transitions quicker, or that in your data that the entropy is lower during these transition phases. But I think from an information point of view, there's also a lot less fun stuff happening. They are experts because they don't need to learn, but also during those transitions, they learn less, which I think is kind of interesting. We have a couple of talks on education coming up in the program, but I think what's strange for me to think of is that experts might therefore not learn during perturbations. Or do you think that they pick up on more subtle changes that we're not capturing, but we just see relative lower entropy in these individuals?
I think that's an interesting observation, and we didn't study the experts in our work, but there's the idea in like studies of expertise and learning that some people develop an adaptive expertise and some people develop a rigid expertise. And in some cases, someone can be really good at doing what they know how to do, except for when something unexpected happens, and then everything sort of breaks down. And so I wonder if this is reflective of that there might even be some distinct subpopulations within experts that we would see that their coordination patterns are also different as a function of how, resilient they are or adaptive.
I like that a lot. The other thought I had, because I really do like your idea of us being more interdisciplinary and being more multimodal, which is again why we are all here, because I wonder if the drivers for change might be observed at one level, and if we're only focusing on one, we might miss it. And I wonder if methodologically speaking, you have ideas of how we would capture that, because typically we look at how two levels sort of covary in time, but we don't necessarily look for how or we don't look necessarily subtly enough at how one might be driving change in another.
I think this is sort of the power or allure of the coordination dynamics approach, that if you have this order parameter, it really tells you all you need to know about the coordination in the system. But if you don't really know what a good parameter might be or where it will come from. That's kind of why I've been advocating for this multi-modality, multi-method approach, so that we can identify what that might be. And the example that I showed about identifying team members that might be the ones particularly driving change, a similar approach could actually be applied to seeing, okay, which is the modality that's sort of driving the changes that we see at a global level, but at this more like fine-grained level.